The light did not arrive as starlight anymore. Somewhere near the beginning of cosmic history, before the sun existed, before Earth had cooled into rock, before there was anything in the universe that could build an eye and call the sky dark, a young galaxy released its light. It crossed space while space itself was stretching. Its colour was pulled longer and longer across billions of years, until what began as the fierce glow of early stars reached us as infrared. Not something a human eye could see, but something a cold mirror could feel. That mirror was James Webb. Webb was not built to admire the universe as it looks now. It was built to receive delayed evidence. It was built to collect light from a time when the first galaxies should still have been small, raw, unstable, and difficult to assemble. The expectation was not emptiness. No serious model imagined a universe with nothing happening. But the first deep views carried a discomfort that could not be dismissed with a shrug. Some of those early systems looked brighter, denser, and more active than the neat version of the timeline had prepared us for. Not impossible. That word is too easy. But early enough to matter. The headline says Webb found a sign of a different universe, something that shattered every model built since Einstein. The real story is sharper than that, because the truth does not need to be inflated. Webb has not opened a door into a parallel cosmos. It has not burned general relativity to the ground. It has done something quieter and more dangerous to our confidence. It has pushed human vision closer to cosmic dawn and shown that the young universe may have been more efficient, more crowded with activity, and less obedient to our simplified expectations than we thought. Stay with this carefully, because the real story is stronger than the headline. If you value space stories that keep the wonder without throwing away the evidence, this is the kind of journey worth subscribing for. The first trap is to imagine science as a row of monuments. Newton, then Einstein, then the Big Bang, then dark matter, then dark energy. Each idea placed on top of the last until the universe becomes a finished structure. But science is not a monument. It is an instrument. It works by being played against reality. A good model does not become sacred because it succeeds. It becomes valuable because it succeeds often enough that its failures become meaningful. That is why Webb matters. A weak model can fail anywhere. A strong model fails in specific places. And modern cosmology is strong. It explains the afterglow of the early universe. It explains why galaxies collect into vast web-like structures. It explains why light bends around massive objects. It explains why the universe has expanded from a hotter, denser state. It has survived more tests than most ideas ever face. So when a new telescope looks into the first few 100 million years and finds galaxies pressing against expectation, the discomfort has weight. The first thing to understand is not the telescope, it is the delay. Astronomy is the science of old messages. Nearby objects speak to us almost in the present. The moon is a little over a second away by light. The sun is about 8 minutes away. But a galaxy in the deep universe is not simply far away. It is far away in time. Its light began travelling when the universe was younger. The farther Webb looks, the more it is not seeing distant places as they are, but ancient places as they were. That already breaks the ordinary sense of distance. Distance becomes history. A point of light becomes a page from an earlier universe. And because space expands while light travels, that page is not delivered in its original ink. The universe stretches the message. Blue light can arrive redder. Ultraviolet light can arrive in infrared. Webb's great advantage is that it was designed for that stretched evidence. It can see what older telescopes could only partly reach. Before Webb, the early universe was not unknown, but it was blurred. Hubble had shown galaxies across staggering distances, including faint traces from very early times. It made deep space feel populated with ghosts. But Hubble was not built primarily for the cold infrared whisper of the first galaxies. Webb is. Its mirror gathers light that has crossed nearly all of cosmic history. Its instruments split that light, measure it, and ask what kind of object could have sent it. That is where the unease begins. In the clean classroom version, the universe cools after the Big Bang. Atoms form. A long, dark period follows. Gravity gathers matter into the first dense regions. Stars ignite, small galaxies appear. Over time, they merge, grow, enrich themselves with heavier elements, form larger structures, and eventually produce the kinds of galaxies we see around us now. The broad outline still stands. The pressure is in the pace. The first few 100 million years were not much time by cosmic standards. They sound enormous to us because human history is tiny. 100 million years can raise mountains, erase species, move continents. But cosmology uses a harsher clock. Galaxies need gas to fall into dark matter halos. Gas must cool. Stars must form. Massive stars must live and die. Their explosions must enrich the surrounding material. Black holes, if present, must grow. Light must escape through gas that was often thick, neutral, and difficult for certain radiation to cross. Every step takes physical work. Then Webb began finding early galaxies and candidates that seemed to ask whether the work had happened faster than expected. Some were brighter than many models predicted. Some appeared compact and intense. Some seemed to sit at redshifts that placed them close to the first chapters of galaxy formation. Some carried hints of mature activity in a universe still young enough that the clock felt tight. That does not mean the measurements are simple. A red object is not automatically ancient. A bright object is not automatically massive. Dust can redden light. Black holes can add brightness. Hot young stars can produce more light per unit mass than older populations. Gravity from a foreground object can magnify something behind it. Strong emission lines can make a galaxy appear brighter in certain filters. Early images can mislead before spectra confirm the distance. Astronomy has learnt to mistrust beauty at first sight. A Webb image can pull the mind forward too quickly. A tiny red smudge appears, and the imagination wants a verdict. Ancient, massive, impossible, revolutionary. But an image alone is closer to a silhouette than a confession. To learn what the object really is, astronomers need its light broken apart. They need fingerprints. That is what spectroscopy gives them. A spectrum spreads light into detail. Atoms leave marks at particular wavelengths. Hydrogen has its signatures. Oxygen has others. If those signatures are shifted far to the red, astronomers can measure how much cosmic expansion has stretched the light. That makes the distance and age estimate much stronger. It can also reveal whether gas is glowing, whether a black hole may be active, whether the object's physical story matches the first dramatic impression. Some early candidates became less dramatic under that pressure. That is not a failure. It is the system working. The universe does not owe us the most exciting interpretation. Some objects first thought to be extremely distant turn out to be closer, dustier, or more complicated. Some mass estimates come down. Some red colours find ordinary explanations. The first wave of surprise gets refined. But the important point is that not everything vanished. Some early galaxies remained early, some remained bright. Some still suggested that star formation in the young universe may have been more sudden, more efficient, or more uneven than expected. The mystery became smaller than the loudest headlines, but stronger than the easy dismissal. It moved from "this breaks everything" to a better question. What did the early universe know how to do that our models had underestimated? That question has teeth. Because a galaxy is not just a light. It is a process caught in the act. Gas falling inward, stars igniting, radiation striking surrounding material, supernovae preparing future chemistry, dark matter holding the invisible frame. If Webb sees bright galaxies near cosmic dawn, then somewhere in that young universe matter gathered, cooled, burned, and changed itself quickly enough to send a signal across almost all of time. The universe may not have broken its rules. It may have used them harder than we expected. And that single shift changes the whole emotional weight of the discovery. A broken rule is simple. A rule used harder than expected is more disturbing, because it means the law was there all along, but our picture of its consequences was too mild. The early universe may not have cheated. It may have been denser, more unstable, more efficient, and more violently productive than the version we carried in our heads. That pulls the story below the visible light. Long before stars made a galaxy visible, dark matter had already begun shaping where that galaxy could form. Dark matter does not shine. It does not make atoms, planets, dust, or fire. It does not cool the way ordinary gas cools. But it has gravity, and gravity is enough to make an invisible skeleton. In the young universe, tiny differences in density became places where matter gathered more strongly. Dark matter formed halos. Ordinary gas fell into those halos. Under the right conditions, the gas cooled, collapsed, and produced stars. Every early galaxy Webb sees is therefore two things at once. It is a visible flare of starlight, and it is evidence of an invisible structure that had to exist first. That makes the timing more demanding. If a galaxy shines early, the dark matter halo must have assembled early enough. The gas must have arrived and cooled. Stars must have ignited. In some cases, heavy elements may already have begun appearing. If a black hole is contributing to the light, then an even stranger chain has to be added. A seed black hole had to form, find fuel, feed rapidly, and shine strongly enough for us to notice from nearly the beginning of time. The visible dot is the last step of a hidden sequence. Webb does not show that sequence directly, it shows the consequence. A red point, a spectrum, an emission line, a brightness that does not sit comfortably where a model expected it. From there, scientists work backward. What halo mass would be needed? What star formation rate? What kind of stellar population? How much dust? How much black hole light? How much magnification? The object becomes a test of how fast invisible structure can become visible history. That is where the pressure sharpens. If the brightness comes from stars, then early galaxies may have converted gas into stars with startling efficiency. If the brightness comes from black holes, then black holes may have grown earlier or more commonly than expected. If the brightness is boosted by gravitational lensing, then some individual objects lose their shock, but lensing itself must be modelled carefully. If unusual stars are responsible, then the first stellar populations may have been more luminous for their mass than the stars we use as familiar guides. None of these answers is boring. They are only less theatrical than a parallel universe. A burst of star formation in a compact young galaxy is not a quiet event. It means gas collapsing under gravity, massive stars igniting in clusters, ultraviolet radiation flooding the surrounding medium, supernovae preparing to tear through the system, and the chemistry of the universe beginning to change. A feeding black hole is not a minor correction. It means matter being driven into a deep gravitational well, heating so fiercely that a small central region can outshine much of its host. The ordinary explanations are already extreme. This is why the story becomes stronger when it refuses exaggeration. If Webb's early objects are partly explained by bursty star formation, that does not make them dull. It means the first galaxies may have lived in flashes. They may have brightened violently, faded, and brightened again. A small galaxy caught during one of those flares could look far more impressive than its average life would suggest. The telescope, seeing across deep time, might catch some systems at their most revealing moment. A human life gives us poor instincts for this. We imagine a galaxy as a thing, stable and named, like an island on a map. But a young galaxy is more like weather around gravity. Gas flows in, radiation pushes out. Stars form, die, and stir the material around them. Black holes feed or starve. A system can change its appearance dramatically depending on when and how we observe it. Webb is not photographing statues. It is catching storms from 13 billion years away. Those storms also change the space around them. After the first atoms formed, much of the universe was filled with neutral hydrogen. For certain kinds of light, this hydrogen acted like fog. The first stars and galaxies began clearing that fog by ionizing the gas around them. The name for this period is reionization, but the physical picture is easier: points of light burning holes through a dark medium. Not everywhere at once, not smoothly, Bubbles formed around early sources, grew, overlapped, and gradually made the universe more transparent. Webb is looking into that uneven clearing. If some early galaxies are brighter or more efficient than expected, they may also have played a larger role in clearing the fog. But brightness alone is not enough. Their radiation had to escape. A galaxy can make energetic light and still trap much of it inside gas and dust. So the question becomes more precise. Not just how many early galaxies existed, but how much of their ionizing light got out. That changes the kind of mystery we are dealing with. It is no longer only a matter of counting galaxies. It is a matter of understanding the pores, cracks, and channels inside young systems. A galaxy could be small but important if radiation escaped efficiently. Another could be bright but less influential if its light was trapped. The first cosmic dawn may have depended not only on spectacular objects, but on countless faint systems whose combined radiation slowly altered the state of space. That is a humbling possibility. The universe's fog may not have been cleared only by the brightest torches. It may have been cleared by embers too faint for us to easily see, working together across enormous volumes. Webb catches the brighter signs first because bright things announce themselves. But the hidden labour of faint galaxies may be just as important. To understand cosmic dawn, astronomers must count both the dramatic and the nearly invisible. This is where early Webb results become a beginning rather than a verdict. The first discoveries widen the territory. The next work must measure the population. Which objects are truly distant? Which are rare? Which are common? Which are powered mainly by stars? Which hide growing black holes? Which are magnified? Which are chemically young, and which already carry dust or heavier elements? Which galaxies let radiation escape into the surrounding hydrogen, and which kept their light trapped inside? The answer will not be one sentence. It will be a census. That census matters because the early universe was not a single environment. It had dense knots and vast empty stretches. Some regions collapsed sooner, some stayed dark longer. Some halos grew large enough to form stars, others remained silent. Cosmic dawn was patchy, local, uneven. A textbook timeline can make it feel like one era replaces another cleanly, but the real universe changed like weather, spreading across a continent at night. Lights in one region, darkness in another. Fog thinning here, thickening there. Storms forming around hidden geography. The hidden geography was gravity. And because gravity began from tiny initial differences, small early advantages could become enormous later consequences. A slightly denser region gathered more matter. More matter deepened the gravitational well. Gas fell in more easily. Stars formed sooner. Radiation changed the surroundings. Mergers brought more fuel. A galaxy grew. The cosmic web emerged not from uniformity, but from slight imperfections amplified by time. Webb is showing us those imperfections after they first became luminous. That is why the title's phrase, "a different universe," can be rescued from its own exaggeration. The universe Webb sees is not different because it belongs to another reality. It is different because it is our reality under conditions we have never experienced. Younger, denser, less chemically mature, more opaque, more uneven, and perhaps more capable of sudden structure than our mature universe intuition allowed. The laws may be continuous. The regime was not. A regime can change what feels possible without changing the rules underneath. Water is still water as ice, liquid, or vapor, but each state behaves like a different world. The early universe was like that. Gravity was gravity, light was light, matter was matter. Yet the conditions were so far from the universe we inhabit now that familiar expectations become poor guides. Gas had fewer heavy elements, space was denser, structures were younger, radiation moved through a medium that was still being transformed. Time was abundant by human standards and scarce by cosmic ones. That scarcity is the quiet pressure behind every Webb image. A few 100 million years sound spacious until the work is listed plainly. First, dark matter must gather enough mass. Then gas must fall in without being blown apart or heated beyond usefulness. It must cool. It must fragment. Stars must ignite. The most massive stars must live, die, and pollute the next gas with heavier elements. If dust is present, some solid grains must form from that enrichment. If a central black hole contributes, a seed must appear and feed. If the galaxy helps clear the hydrogen fog, energetic light must escape into the wider universe. Nothing in that chain is magic, but the chain is long. So when Webb finds systems that seem to have already completed several links, the discomfort is not theatrical, it is mechanical. The question becomes whether each link can be tightened enough to fit inside the available time. Maybe yes, but the answer has to be earned in detail, not assumed because the broad model works elsewhere. This is why early galaxies are not just objects, they are clocks with light coming out of them. Their brightness, colour, spectra, and chemical hints all tell us how fast the machinery may have run. A galaxy rich in young massive stars says one thing, a dusty source says another. A compact object with signs of an active black hole says another. A spectrum with strong hydrogen emission says still another. Webb does not simply show that something existed, it gives astronomers a way to ask what physical history had to occur before that light could be released. Sometimes the answer is less extreme than the first image suggested. That matters. A responsible story must leave room for objects to become ordinary under inspection. Some candidates will not survive. Some will move to lower redshift. Some will lose mass. Some will turn out to be bright for reasons that do not require a huge population of stars. This pruning is not an embarrassment. It is the cost of seeing farther than before. When a new instrument opens a new frontier, the first map is always crowded with things that need to be renamed. The remaining objects are the ones to watch. They are the ones that keep their distance after spectroscopy, the ones that remain luminous after dust, lensing, and black hole contamination are considered, the ones that appear in enough numbers to become a population rather than a curiosity, the ones that simulations struggle to produce without turning some dial too far and breaking a later observation. That last constraint is severe. A model cannot make the early universe busy by ruining the rest of cosmic history. If it forms too many stars too quickly, it may overproduce later galaxies. If it grows black holes too easily, their descendants may not match what we observe nearby. If it changes dark matter behavior, the cosmic web responds. If it alters expansion history, the microwave background notices. Every fix travels. Nothing stays politely inside the box where it was introduced. The universe is connected too tightly for convenient repairs. This is why the Hubble tension has such a different weight. Early galaxy brightness may be solved by better astrophysics. The expansion mismatch reaches closer to the scaffolding. One method begins with the ancient universe, especially the cosmic microwave background, and uses the standard model to infer how fast space should be expanding today. Another method builds outward from nearby distance markers, through stars and supernovae, and measures expansion more directly in the local universe. The two answers are close. Close enough to show that the model is powerful. Not close enough to be comfortable. The difference is not a giant failure you can see with the naked eye. It is a precise disagreement inside a mature measurement system. That is why it has lasted. If the mismatch were enormous, it might already have an obvious cause. If it were tiny, it might dissolve into uncertainty. Instead, it sits in the uncomfortable middle, too persistent to ignore, too subtle to explain casually. Webb entered that problem like a judge checking one witness. Maybe older distance measurements had been biased. Maybe stars used as distance markers were blended with nearby stars in Hubble images. Maybe dust or crowding made some objects look brighter than they were. Webb's sharper infrared view could test part of that. If the tension disappeared under better resolution, cosmology would breathe easier. The disagreement would become an instrumental story, not a cosmic one. It did not disappear. That does not prove new physics. It removes one simple escape. There is a difference. Science advances through that kind of narrowing. A door closes and the hallway becomes more defined. The field is left with fewer comfortable explanations not with permission to believe anything. This is where the phrase "shattered every model" fails most badly. Models are not glass ornaments, they are tools with ranges. Newton's gravity still works well enough to send spacecraft across the solar system, even though Einstein revealed a deeper structure. Einstein's gravity still works across an extraordinary range, even though cosmologists debate dark energy, dark matter, and the expansion tension. A model can be incomplete without being worthless. It can be wrong at the edge and still reliable in the center. The real question is where the edge begins. Webb may be showing us one edge in galaxy formation. The Hubble tension may be pointing toward another edge in cosmic expansion. They may remain separate. They may partially connect. No honest account can force them together before the evidence does. But it is fair to say that the confidence of the old smooth picture has changed. Cosmic dawn is no longer a blank interval where assumptions can spread comfortably. It is becoming populated with measurements. Once an era has measurements, it can resist us. That resistance is the real drama. Not a universe breaking into fantasy, but a universe refusing to be simplified at the exact point where our best theories want to become elegant. Elegance is powerful, but it is not evidence. The sky gets the final vote, and the sky Webb sees near the beginning is not quiet. It contains early galaxies bright enough to sharpen old questions. It contains compact red sources that may mix dense stars, dust, and growing black holes. It contains signs of gas being lit and altered while the universe was still clearing its fog. It contains enough uncertainty to prevent easy conclusions, and enough structure to prevent easy dismissal. That combination is rare. Pure ignorance is dark. Pure certainty is closed. Webb has given us something more useful. A frontier with coordinates. A frontier with coordinates is harder to ignore than a mystery with a dramatic name. It gives scientists places to return to, a field in the sky, a redshift to confirm, a spectrum to deepen, a simulation to rerun, a population to count again when the telescope has more time. The unknown stops floating above the subject like fog and begins attaching itself to objects. That is when a question becomes dangerous to a model, because it can be measured from more than one direction. Webb has made cosmic dawn measurable in that way. Not completely, not cleanly, but enough that the earliest galaxies can now argue with theory. A galaxy only a few 100 million years after the Big Bang can ask whether gas cooled quickly enough. A compact red source can ask whether black holes were already feeding. A bright emission line can ask how much radiation escaped into the surrounding hydrogen. A group of unusually luminous objects can ask whether the first surveys are seeing rare flares or a real population. The answers will not arrive together. Some will come from deeper Webb observations, some from wider surveys, some from ground-based telescopes studying related objects at slightly later times, some from simulations rebuilt with harsher early conditions, some from future instruments that will map neutral hydrogen more directly and show how the cosmic fog actually disappeared. The story will become less clean before it becomes clearer. That is normal. A new window rarely gives one simple view. It gives clutter. A room thought to be empty turns out to contain furniture, dust, tools, old papers, broken glass, and footprints crossing in different directions. The first mistake is to point at one footprint and explain the whole room. The second mistake is to call the room meaningless because it is messy. The real work is slower. Identify what belongs together, what is accidental, what is foreground, what is background, and what changes the story of the house. Cosmic dawn is that room. The brightest early galaxies are not automatically the most important. They are the easiest to notice. The faint galaxies may have carried much of the burden of reionization. Black holes may have shaped some systems while leaving others untouched. Dust may be present in pockets but absent elsewhere. Some galaxies may burn in short episodes, so a survey catches them in a temporary blaze. Others may remain faint, numerous, and collectively powerful. That unevenness prevents the old smooth picture from returning unchanged. It also prevents the new picture from becoming a slogan. The early universe was not simply too bright. It was selective, patchy, biased by what we can see, violent in some regions, quiet in others. The telescope receives whatever survived the journey, then our models must infer the rest. Every strong claim has to pass through that filter. There is no shortcut around it. This is where Einstein enters the story, with more dignity than the headline gives him. Einstein did not build a catalogue of first galaxies. He did not know about dark matter halos, reionization histories, little red dots, or infrared spectra from cosmic dawn. What he gave science was deeper, a way for space-time itself to participate in physics. Gravity became geometry. Light followed curved paths. The universe could expand as a whole. Black holes moved from mathematical possibility to physical reality. Modern cosmology grew inside that language. So Webb is not looking at Einstein from the outside. It is using an Einsteinian universe to test the later structures built within it. Redshift, distance, lensing, black holes, expansion, the very tools used to understand Webb's discoveries depend on the framework that the headline pretends has simply been shattered. If something changes, it will not be a cheap overthrow. It will be a refinement inside a tradition strong enough to make the problem visible. That distinction matters because bad science storytelling loves replacement myths. It wants every discovery to kill the old world. But the best theories usually do not die like villains. They become limited. Newton did not vanish when Einstein arrived. Newton became the truth of a certain regime: slow speeds, weak gravity, ordinary scales. Einstein gave a deeper frame, but the old equations still guide spacecraft with astonishing accuracy. If cosmology changes again, the likely result will not be that everything before was foolish. It will be that our current model becomes the clean approximation of a richer one. The question is whether Webb and the Hubble tension are pointing toward that richer one. No one can say honestly yet. The safer path is astrophysical revision. The first galaxies may need more efficient star formation. Black hole seeds may need to be heavier or more common. Early stellar populations may need different assumptions. Feedback in small galaxies may behave in bursts rather than steady regulation. Dust may form earlier in some systems. Radiation may escape through channels carved by violence. These changes can make the young universe more active without changing gravity or the basic expansion model. The deeper path touches cosmology itself. If the expansion mismatch remains after every local measurement is checked and rechecked, then some ingredient in the early universe inference may be incomplete. Early dark energy is one possibility people examine. Modified dark matter behavior is another broad family. Changes to gravity at cosmic scale are harder because general relativity is so well tested, but they are part of the landscape of ideas. Each proposal faces the same brutal test. It must solve the problem it targets without damaging everything the old model already explains. A theory does not earn belief by sounding profound. It earns belief by surviving constraints. That is why most proposed solutions fail. They help one number and hurt three others. They ease the Hubble tension and spoil the microwave background. They speed up early structure and overgrow later galaxies. They adjust expansion and distort lensing. The universe is a tight accounting system. You cannot hide a change in one era without leaving fingerprints elsewhere. This tightness is frustrating and beautiful. It means reality has consistency. It means the universe is not a pile of unrelated facts. The first galaxies, the background radiation, the cosmic web, supernova distances, black holes, chemical enrichment, galaxy clustering, and today's expansion rate all belong to the same history. A change near the beginning sends consequences forward. A measurement nearby can argue with an inference from the ancient sky. That is why Webb's faint red dots can sit in the same conversation as a number describing cosmic expansion. They are different kinds of evidence, but they live in one universe. The human mind wants to separate them because one is visual and the other is numerical. A galaxy feels like a thing. The Hubble constant feels like an abstraction. But both are ways of reading time. The galaxy tells us what structure had already formed by a certain age. The expansion rate tells us how the scale of space changed between then and now. If either reading is wrong, the timeline shifts. If both readings remain strained, the timeline becomes a suspect. Not wrong. Suspect. That word keeps the story honest. A suspect has not been convicted. It has reasons to be examined. The early universe now has reasons to be examined with less comfort than before. Its galaxies are no longer imaginary placeholders between the microwave background and later cosmic history. They have brightness, colours, spectra, sizes, possible black holes, and effects on surrounding gas. They can no longer be treated as a thin prelude. They are becoming a chapter with evidence of its own. And chapters with evidence can change the whole book. But the book cannot be rewritten from one page. That is the discipline the subject demands. Webb has opened a chapter that was previously faint, compressed, and partly inferred. It has not handed us the final edition. The earliest galaxies now have enough detail to challenge expectations, but not enough to allow careless certainty. Every strong claim must pass through a sequence of tests: distance, brightness, mass, source of light, environmental effect, population size, and consistency with everything that comes later. The most important word here is consistency. A galaxy at cosmic dawn cannot be understood alone. It must fit into the growth of structure before it and after it. It must arise from initial density ripples that also produce the cosmic web. It must live inside a dark matter halo whose descendants affect later galaxies. Its stars must contribute to chemical enrichment without overproducing what we observe later. Its radiation must help reionize space without making the universe transparent too soon. If it contains a black hole, that black hole must grow into a population that makes sense at later times. One early object can be dramatic. A connected history must be accountable. That accountability is where the model earns or loses trust. It is easy to make a simulation produce a few bright early galaxies by turning up star formation. It is harder to do that while also matching the galaxies we see after billions of years. It is easy to invent a new early energy component to ease one expansion problem. It is harder to keep the microwave background, galaxy clustering, lensing, and element abundances intact. The universe does not reward isolated fixes. It punishes them across time. This is why the current moment feels tense rather than chaotic. There are enough anomalies to disturb confidence, but enough structure to prevent intellectual freefall. Scientists are not staring at random contradictions. They are tracing pressure through a connected system. Early galaxies press on star formation and black hole growth. Reionization presses on faint populations and escaping radiation. The Hubble tension presses on the expansion history. Each problem has its own path. Each path crosses the same underlying landscape. That landscape is the standard cosmological model. It is often described with a few ingredients: ordinary matter, dark energy, radiation, initial fluctuations, expanding space-time. The simplicity of the list can be misleading. Ordinary matter alone contains gas physics, stars, chemistry, dust, explosions, magnetic fields, and black holes. Dark matter shapes structure without showing itself directly. Dark energy dominates the late expansion, while remaining physically mysterious. The initial fluctuations are tiny in the beginning and enormous in consequence. So when Webb challenges the model, it is not striking a single wall. It is probing a house full of rooms. Some rooms are sturdier than others. The broad evidence for an expanding universe is not fragile. The need for unseen gravitational matter is not based on one observation. The success of the cosmic microwave background fit is not a casual coincidence. But the detailed story of how the first galaxies turned gas into light is less settled. That is the room Webb entered with a torch. The torch revealed clutter, not collapse. Clutter can still be revolutionary if it was absent from the old floor plan. A room that was drawn empty may contain machinery. If the machinery is small, the map only needs editing. If the machinery connects to the foundation, the architect has work to do. Webb's early galaxies are that kind of discovery. They may require better astrophysics. They may hint at deeper changes. The field is now trying to learn which is true, without mistaking speed for insight. The most visible clue remains early brightness. A luminous source close to cosmic dawn asks how light was produced so efficiently. If young stars dominate, then the early stellar population may have been hotter, heavier, or more concentrated than assumed. If emission lines contribute strongly, then gas was being ionized in intense regions. If dust is present, then earlier generations of stars had already died and enriched the system. If a black hole sits at the center, then gravity built a compact engine before the cosmic clock had advanced very far. Each option is an origin story. Stars explain light through nuclear fire. Black holes explain light through falling matter. Dust explains color through prior death. Lensing explains brightness through curved spacetime. A single red point may contain several of these at once. That is why Webb's images, beautiful as they are, can be misleading if treated as photographs in the ordinary sense. They are not portraits. They are compressed evidence. A portrait shows a face. A Webb dot shows a puzzle made of time, distance, chemistry, gravity, and light. The work of interpretation is to unfold that puzzle without tearing it. Astronomers compare the observed light to possible histories. A very young, intensely star-forming galaxy may reproduce one set of colours. An older, dusty galaxy may reproduce another. A galaxy with an active black hole may imitate both in certain bands. Spectra reduce the ambiguity, but do not always erase it. Some answers remain probabilistic, some require deeper exposure. Some require a larger population before one object can be understood in context. That context is growing. The early universe is no longer represented by a few heroic detections. Webb surveys are building samples. Samples allow patterns. Patterns allow tension to be measured instead of felt. If the number of bright galaxies remains higher than expected, the model must respond. If the apparent excess shrinks with better measurements, the story changes. If black holes account for much of the light, one crisis moves into another channel. If faint galaxies prove numerous enough to explain reionization, the cosmic fog becomes less mysterious, but the efficiency of early star formation still matters. Nothing stands still. That is the danger of trying to freeze the Webb story into one claim. The discovery is not finished. It is moving. New spectra arrive. New candidates are confirmed. Old estimates are revised. Simulations adapt. Observers and theorists argue across the gap between what is seen and what can be produced. The best version of the narrative must preserve motion, because the science itself is in motion. Still, the direction of the motion is clear enough to feel. The early universe is gaining texture. It is not a blank, dark corridor between the microwave background and later galaxies. It has structure, bursts, sources, fog, possible black holes, and chemical hints. It is becoming a place with internal variety. The word dawn can make it sound gentle. Webb is replacing that softness with something harsher. Cosmic dawn was not only light arriving, it was matter under stress becoming visible. That stress reaches into the meaning of time. Human time is measured by experience, days, years, generations. Cosmic time is measured by transformation. How long does it take gravity to gather matter? How long before gas can cool? How many massive stars must die before dust appears? How soon can a black hole become influential? How quickly can scattered sources change the transparency of intergalactic space? Webb's early galaxies compress those questions into faint signals. They make the first billion years feel less like a waiting period and more like an engine starting under load. The pistons are dark matter, gas, radiation, and gravity. The sparks are first stars. The exhaust is enrichment. The heat is feedback. The smoke is dust. The machine does not run smoothly. It coughs, flares, stalls, restarts, and throws material back into the space around it. That image matters because it protects the story from false calm. The early universe was not serene just because it was young. Youth in cosmology can mean instability. It can mean conditions changing quickly. It can mean small systems forming in a medium that has not yet been softened by later generations. It can mean rare, dense regions racing ahead, while most of space remains dark. The first galaxies were not miniature versions of modern galaxies. They were experiments being performed by gravity under ancient conditions. Some experiments failed. Some remained invisible. Some sent light to Webb, and that fact alone changes the scale of the question. A failed early galaxy leaves little for us to read. A faint one may remain below the telescope's reach. A system hidden behind too much gas may do important work without announcing itself clearly. The galaxies we see are therefore not the whole population. They are the visible edge of a larger process. Any model that explains only the bright edge may still miss the machinery underneath. That is why the faint end matters so much. The brightest galaxies attract the eye, but the faintest galaxies may have carried much of cosmic dawn. If they were numerous, and if enough of their energetic radiation escaped, they could have helped clear the hydrogen fog, even without looking spectacular individually. In that case, the universe's transformation depended on a crowd of small sources, not only on a handful of brilliant ones. Webb can begin to measure that crowd, but even Webb reaches limits. Some of the most important lights may sit just beneath detection, shaping history from the edge of visibility. That possibility has a different emotional force from the headline. It is not one shocking object overturning everything. It is an entire hidden population changing the meaning of an era. It suggests that cosmic dawn may have been built less like a monument and more like a fire spreading through dry grass. Countless small points joining into a larger change. The first galaxies did not need to look grand to matter. They only needed to be numerous, hot, and leaky enough for their radiation to escape. Leaky is not an elegant word, but it is the right kind of word. A young galaxy can produce ultraviolet radiation, yet keep much of it trapped. Gas absorbs, dust interferes, dense clouds block pathways. But feedback can carve openings. Supernovae can blast channels. Radiation pressure can thin regions around young stars. If enough holes open, ionizing light escapes into intergalactic space and begins changing hydrogen beyond the galaxy. The fate of cosmic fog may depend on the internal damage done by stars to their own birthplaces. Creation makes escape routes by violence. That gives reionization a physical texture. It is not just an era with a name. It is the result of light fighting its way out of young galaxies, one region at a time. The early universe was not simply turning transparent, it was being pierced. Around some sources, bubbles of ionized gas expanded. Around others, radiation stalled. Over time, those bubbles grew, overlapped, and changed the conditions through which later light could travel. Webb is catching pieces of that transformation. A galaxy with strong hydrogen emission is not only bright, it may be telling us about the gas around it, the radiation inside it, and the state of the surrounding universe. If the light appears where the fog should have been thick, then something nearby may have cleared a path. That does not prove one simple scenario. It opens a local crime scene. What produced the radiation? How did it escape? And what was the surrounding hydrogen doing at that moment? The power of Webb is that it turns cosmic eras into local questions. Instead of asking only when reionization happened, astronomers can ask what this galaxy did to this patch of space. Instead of asking only when galaxies began, they can ask how this object made this much light with this much time available. Instead of speaking of early black holes as a category, they can examine compact red sources and ask whether some contain active centers. The grand story breaks into testable fragments. That is how a field becomes sharper. A vague mystery can support almost any interpretation. A sharp mystery restricts the imagination. It says, here is the redshift, here is the brightness, here is the spectrum, here is the uncertainty. Now build a history that can survive those facts. The freedom narrows, the story improves. This narrowing is happening at the same time that the larger cosmological tension refuses to vanish. The Hubble tension sits quietly behind the early galaxy debate like a second rhythm. It does not explain every Webb surprise. It should not be used carelessly as a master key. But it changes the atmosphere. If only the first galaxies looked unusual, the safest conclusion would be early astrophysics. If only the expansion rate disagreed, the focus would remain on distance measurements and early universe inference. Together, they make the first chapters of cosmic history feel less settled than the polished diagrams suggest. Still, connection is not the same as cause. A disciplined script must hold that line. The early galaxies may be solved by better star formation physics. The compact red dots may become a mixed population, not a single new category. The Hubble tension may eventually trace back to subtle systematics in one or more methods, or some part of the tension may remain and force a deeper addition to the model. The honest field of possibility is wide, but not limitless. The universe is allowed to surprise us. It is not allowed to become whatever a headline wants. That is why the strongest version of a different universe is not a multiverse claim. It is a regime claim. Webb is showing us a phase of our own universe where density, chemistry, radiation and structure had not yet settled into the patterns familiar from later times. The universe was not different in law, it was different in state. Like iron heated until it glows, it was the same substance behaving under conditions that make it look transformed. In that state, our everyday intuition fails. We are used to a universe where galaxies have had billions of years to grow. We are used to stars forming inside material already enriched by previous stars. We are used to space being transparent across vast distances. We are used to black holes as ancient central monsters in mature galaxies. Webb asks us to imagine the earlier version, gas still close to primordial in many places, radiation struggling through fog, galaxies forming in compact bursts, black holes possibly appearing before their surroundings look ready for them. It is not less real because it feels unfamiliar. The unfamiliar is where models earn their keep. A model trained mostly on later galaxies may misjudge the first ones. A simulation calibrated to reproduce mature cosmic structures may need sharper treatment of early feedback. A stellar population model built from known stars may struggle if the first stars were hotter, heavier, or more short-lived. A black hole growth scenario that works comfortably over billions of years may become strained when the clock is compressed. None of this requires panic. It requires better accounting. And the accounting is already becoming more severe. Astronomers no longer ask only whether a galaxy exists at high redshift. They ask how certain the redshift is, whether the spectrum confirms it, whether emission lines affect the brightness, whether stellar mass has been overestimated, whether the galaxy is magnified, whether there is evidence for an active nucleus, whether the object belongs to a broader luminosity function, whether simulations can reproduce its kind without damaging later epochs. Each question cuts away a weak interpretation. What remains is more valuable. This is how Webb's first shocking images will mature into science, not by staying shocking, but by becoming unavoidable or dissolving. The objects that dissolve still teach us how the telescope can be fooled. The objects that remain teach us how the universe works. Both outcomes matter, but only the remaining pressure can reshape the model. And the pressure has not yet finished accumulating. The pressure accumulates because the same young universe keeps refusing to stay simple. Every new confirmed object narrows the room for easy explanations. A single galaxy can be rare, a handful can be a selection effect. A broader population begins to shape the rules. If enough early galaxies are bright, then the first star-forming systems were not merely present, they were productive. If enough compact red sources hide black holes, then black hole growth was not a late luxury of mature galaxies. If enough faint systems exist below the bright detections, then reionization may have been carried by a crowd we are only beginning to count. The old image of cosmic dawn was too smooth. Webb is replacing it with texture. Texture is harder to model because it resists averages. A smooth story can say galaxies gradually formed, stars gradually enriched matter, radiation gradually cleared the fog. But the telescope sees hints of a rougher process. Bursts instead of smooth growth, local bubbles instead of uniform clearing, compact engines instead of slow assembly, dust in some places, pristine gas in others, black holes possibly sharing the stage with stars much earlier than expected. That roughness may turn out to be the main discovery. Not one impossible galaxy. A universe whose first visible structures behaved unevenly enough that average expectations misled us. That matters because cosmological models often begin with smoothness and then grow complexity. The early universe, in the largest sense, was remarkably uniform, with tiny ripples that later became structure. But once gravity begins amplifying those ripples, smoothness does not remain the emotional truth. Matter falls into filaments. Filaments feed halos. Halos host galaxies. Galaxies ignite, explode, and disturb their surroundings. The clean beginning becomes a violent network. Webb is looking at the moment the network first begins to shine. That shine is not passive, it changes the network. Early stars do not simply mark where gas collapsed, they feed energy back into the gas. They heat it, ionize it, push it, pollute it, sometimes shut down further star formation, sometimes trigger more. A black hole feeding in a young galaxy can add another source of energy and disturbance. The first luminous objects were therefore not decorations placed on a dark skeleton. They were actors changing the stage. This is one reason the early universe is so difficult to simulate. Gravity is relatively clean compared with everything that happens after gas becomes involved. Gas can cool, gas can shock, gas can fragment. Stars form inside dense regions that simulations cannot always resolve directly. Massive stars release radiation and winds. Supernovae explode. Dust forms and absorbs light. Black holes accrete matter through processes too small to follow in cosmic volumes. To model a galaxy across billions of years, scientists must represent some of this physics through recipes. Those recipes are not guesses, but they are not final truths. They are bridges between scales. Webb is testing those bridges where they are most exposed. A recipe calibrated on later galaxies may not work in metal-poor gas near the beginning. A feedback model tuned for mature systems may misrepresent tiny early galaxies with shallow gravity. A stellar population assumption based on better-known environments may understate the light from hotter, more massive early stars. A black hole seeding prescription may be too slow for compact red sources if many of them turn out to host active nuclei. The telescope is not only showing objects, it is auditing assumptions. An audit is less dramatic than an explosion, but it can be more consequential. It asks where the numbers came from. It asks why a simulation expected fewer bright galaxies. It asks whether the assumed relation between halo mass and starlight was too cautious. It asks whether the earliest stars were treated too much like later ones. It asks whether black holes were allowed to appear through enough pathways. Each answer has a cost. Make star formation too efficient, and later galaxies may become too massive. Let black holes grow too easily, and their later population may become wrong. Allow too much radiation to escape, and reionization may happen too early. Add a new cosmic ingredient, and the microwave background may object. A good fix must move through the entire history without leaving damage. That is why the real drama is not discovery, but compatibility. The universe has to remain one story. The first galaxies cannot have one set of rules, while later galaxies obey another, unless the changing conditions explain the difference. Expansion cannot be adjusted in the early universe without altering the ruler used to interpret the cosmic microwave background. Dark matter cannot be changed only when convenient. Dark energy cannot be made flexible without consequences. Every solution must pay its debts in other observations. This is the severe beauty of cosmology. Nothing is truly isolated. A faint galaxy at high redshift, a temperature ripple in the microwave background, a supernova in a nearby galaxy, a cluster bending light, a quasar powered by an early black hole. all are pieces of one reconstruction. They speak from different times. They use different methods. They carry different uncertainties. But they are not separate universes of evidence. They are one universe seen through different surviving traces. That is why a mismatch can become so powerful. If one trace disagrees, you check the trace. If several traces lean against the same comfortable picture, you check the picture. Not by throwing it away, but by asking which part of it was overconfident. In the Webb era, that overconfidence may live in the details of early star formation. It may live in black hole seeding. It may live in how radiation escapes. It may live in the inferred expansion history. Or it may be divided among several smaller corrections that only look like one large crisis from a distance. The danger is choosing the answer too soon. A viewer wants resolution. A headline wants impact. A field wants clarity. But the universe has not yet supplied the final shape. The most honest response is to stay inside the tension without exaggerating it. Webb has not ended cosmology. It has made cosmology less comfortable. That is more valuable than a false apocalypse. A false apocalypse burns fast and leaves nothing. A real tension keeps working. It changes where telescopes look next. It changes how simulations are built. It changes which objects receive follow-up spectra. It changes how scientists think about the first stars, the first black holes, the escape of radiation, and the pace of chemical enrichment. It teaches the field which old simplifications were harmless and which were hiding important physics. Even the objects that lose their drama help. A candidate revised downward in distance teaches caution. A mass estimate reduced by better modelling teaches humility. A red source explained by a black hole teaches that early galaxies can disguise their power. A lensing correction teaches that gravity itself can distort our census. Each correction improves the map. The goal is not to preserve shock. The goal is to locate truth. Truth, in this subject, often arrives smaller than excitement and larger than expectation. Smaller because many dramatic first claims soften. Larger because the surviving pattern reaches deeper. The surviving pattern here is that cosmic dawn was physically rich. It contained enough activity to challenge lazy simplicity. It was not a blank stage waiting for later galaxies to become interesting. It was already building, burning, clearing, enriching, and perhaps feeding black holes. The first billion years were not merely the universe preparing for history, they were history. That changes the way the whole timeline feels. The familiar universe, stars, galaxies, planets, chemistry, observers, does not emerge after a long, empty pause. It begins its chain of possibility early, in compact systems so faint that their light reaches us only as a technical achievement. Those systems may not look grand in the images. They may be dots, smears, red hints, but some of them mark the first successful attempts by matter to become luminous structure. That is enough to make the silence before them feel different. Not empty. Waiting under pressure is a very different image from emptiness. It suggests that the Dark Age was not a pause, but a preparation hidden from ordinary sight. Gravity was already deepening tiny density differences. Gas was already finding the wells it would later fall into. Dark matter was already building the invisible geography of future galaxies. Nothing looked like the later universe yet, but the conditions for later light were tightening. The first stars did not appear from nowhere. They appeared because the dark had been organizing itself. That is why Webb's earliest galaxies feel so consequential. They are not simply objects placed near the beginning. They are the first visible proof that hidden organization had crossed a threshold. A dark matter halo became deep enough. Gas became dense enough. Cooling became effective enough. Stars became hot enough. Radiation became strong enough to escape into time. A faint dot in a Webb image is the visible surface of that whole chain. The chain is what models must now reproduce. Not just a redshift, not just a brightness, not just an attractive image for a press release. A real explanation must account for the conditions that allowed that object to exist when it did. It must explain why enough gas became stars, why the light looks the way it does, whether dust was already present, whether a black hole was involved, whether the object is rare or part of a larger population, and how such systems fit into the later growth of galaxies. That is a heavy burden for a dot. But deep astronomy is full of heavy dots. A point of light can contain a star. A red smear can contain a galaxy. A tiny distortion can reveal dark matter. A slight mismatch in a number can expose a missing ingredient in a theory. Scale fools the eye. What looks small in an image may carry enormous explanatory weight, because it comes from a place in time where evidence is scarce. Scarcity makes every confirmed signal more valuable. The first confirmed galaxies near cosmic dawn are like surviving letters from a burned archive. You do not build the whole history from one letter, but you also do not ignore it because it is small. You read its date, you study the ink, you compare the handwriting. You ask who could have written it, what had to exist for it to be written, and why it survived when so much else is gone. Webb has not found the whole archive. It has found enough pages to prove the archive is not empty. The difficulty is that some pages are smudged. A spectrum can clarify, but distant spectra are hard. Light is faint, exposure time is precious. Multiple physical scenarios can overlap. A galaxy's apparent maturity may depend on assumptions about its stars. Its colour may depend on dust. Its brightness may depend on an active centre. Its distance may depend on identifying the right spectral feature. Even strong data require judgment. This is where trust enters the narration. The trustworthy story does not pretend the uncertainty is a flaw. It shows why uncertainty exists, then keeps moving. Early universe astronomy is difficult because the evidence is thin and ancient, not because the field is careless. Webb gives better evidence than ever before, but better does not mean complete. The telescope has sharpened the frontier, it has not flattened it. A sharpened frontier cuts both ways. It cuts through lazy hype by showing which claims do not survive better measurement. It also cuts through lazy confidence by showing that some surprises remain. If all the early tension had vanished after spectroscopy and better modelling, the story would become simple. Webb would have taught us caution and little more. If every dramatic object had stayed impossible, the story would become simple in another direction. The model would be an obvious crisis. Instead, the field sits in the harder middle. Enough corrections to humble the first excitement, enough surviving pressure to keep the old picture from relaxing. That middle is where real science lives. It is uncomfortable because it gives no clean emotional release. The universe is not announcing that the model is dead. It is not reassuring us that nothing important happened. It is offering a mixed signal and demanding finer thought. Some early galaxies may be less massive than they first looked. Some may still be unusually luminous. Some compact red sources may turn out to host black holes. Some may not. The first populations may be more diverse than the categories we brought to them. Diversity at cosmic dawn matters because it changes how beginnings work. A simple beginning is easy to narrate. First stars, then galaxies, then larger galaxies, then the familiar universe. A diverse beginning is messier. Some places race ahead, others lag. Some sources clear their surroundings, others remain buried. Some black holes feed early, others wait. Some starbursts flare and fade. A small telescope field may catch a rare overactive region and make the young universe look more extreme than the average. Wider surveys may smooth the picture, but they may also reveal that the extremes were not so rare. Either way, the old average is no longer enough. The physical reason is that gravity amplifies difference. The early universe began with tiny ripples. On the largest scales it was smooth, but not perfectly smooth. Those small differences became destiny. Slightly denser regions gathered matter faster. Faster growth led to earlier halos. Earlier halos gave gas a place to collapse. A few regions crossed the threshold into starlight before others. Once light appeared, it changed the rules nearby by heating gas, ionizing hydrogen, and injecting heavy elements through stellar death. The first bright places were not merely early. They were influential. An early galaxy that forms stars fiercely can affect its neighbourhood. It can carve a bubble in the neutral hydrogen. It can enrich nearby gas. It can send radiation into intergalactic space. If it hosts a black hole, it can add harder radiation and energetic outflows. These local effects feed back into the larger history. Cosmic dawn is therefore not only a record of when galaxies appeared, it is a record of how the first luminous systems began altering the environment from which later systems formed. That is why the word dawn is almost too gentle. A dawn on Earth is smooth to the human eye. The sky brightens, shadows retreat, colours appear. Cosmic dawn was not like that. It was torn open in patches. Light appeared around dense knots. Fog resisted. Radiation escaped through channels. Some regions became transparent while others remained opaque. The universe did not brighten like a sky. It blistered with sources. That image carries the right kind of unease. Not panic, not spectacle. Physical unease. Matter under gravity creating concentrated violence. Light struggling through gas. Time compressed near the beginning. The first stars and galaxies not as delicate candles, but as engines that damaged their surroundings enough for their light to get out. And this brings the story back to Webb itself. Webb is not seeing cosmic dawn directly as it happened everywhere. It is sampling surviving light from selected regions, translated through expansion into infrared. It catches the scars and signals available from our position. The telescope is extraordinary, but it is still a witness with a particular vantage point. It sees what cosmic history allows to reach us. That limitation is not a weakness. It is the condition of all astronomy. We never hold the universe in our hands. We receive traces. We compare them. We build the most coherent account we can. Then a better instrument arrives, and the account must face new testimony. Webb is new testimony from the edge of the visible beginning. And the testimony is not finished. The testimony is not finished because the witness is still speaking. Each new observation adds another constraint. A deeper spectrum can turn a candidate into a confirmed galaxy, or move it out of the earliest era entirely. A wider survey can reveal whether a bright object was rare luck or part of a common population. A better model can reduce a mass estimate without erasing the object's importance. A black hole signature can move the mystery from star formation into early gravitational growth. The story changes as the evidence sharpens. But the pressure does not disappear simply because the first dramatic version gets corrected. That is the important distinction. Correction is not cancellation. A galaxy can become less massive and still be surprising. A source can turn out to include black hole light and still deepen the early growth problem. A red object can be partly explained by dust and still imply earlier stellar death. A population can shrink in number and still remain too active for the simplest expectations. The first interpretation may fall, while the deeper question survives. The deeper question is pace. How fast did the universe become capable of building luminous structure? Not in a broad philosophical sense, but physically. How soon did dark matter halos become large enough? How efficiently did gas turn into stars? How quickly did the first stars enrich their surroundings? How early did black holes appear as visible engines? How much radiation escaped into intergalactic space? How did all of this happen while expansion was stretching the background and neutral hydrogen was still shaping what light could travel? These are not separate curiosities. They are linked gears. Turn one and the others resist. If star formation was more efficient, feedback becomes more important because young stars would disturb their gas more violently. If feedback carved channels through gas, radiation could escape more easily and contribute to reionization. If black holes were common early, they may have affected both the brightness of galaxies and the ionization of surrounding gas. If early galaxies were less massive than first thought, but still bright, then the first stars may have produced more light per unit mass than later assumptions allowed. Every answer changes the next question. That is why a list of discoveries is not enough. The meaning lives in the dependencies. Webb is not simply finding old galaxies, then red dots, then hydrogen lines, then expansion-related tensions. It is forcing these things to speak to one another. A young galaxy's brightness is connected to its stars. Its stars are connected to its gas. Its gas is connected to its halo. Its halo is connected to dark matter. Its radiation is connected to the fog around it. Its distance is connected to cosmic expansion. The whole chain has to hold. The chain may hold, but not loosely anymore. The early universe is tightening the tolerances. Models that once had room to breathe are being asked to fit sharper evidence. A simulation cannot merely produce galaxies eventually, it must produce the right kinds of galaxies early enough, without producing too many later. A model of reionization cannot merely say early sources cleared the fog. It must identify which sources, how many, how bright, and how much radiation escaped. A solution to the Hubble tension cannot merely adjust one number. It must pass through the entire archive of cosmic evidence without tearing it. This is the current moment feels so alive. The field is not floating in speculation. It is constrained from all sides. The microwave background watches the early expansion. Galaxy surveys watch structure. Webb watches the first luminous systems. Supernovae and distance markers watch the local expansion. Lensing watches gravity and mass. Element abundances watch the hot early universe. Each record permits some changes and rejects others. The universe is generous with clues, but severe with excuses. That severity is what separates real frontier science from empty mystery. Empty mystery grows when evidence is missing. Real mystery grows when evidence is good enough to create conflict. Webb's deepest value is not that it made the universe vague. It made a vague era specific enough to be troublesome. Specific trouble is precious. It tells scientists where to aim next. If a source may host a black hole, look for broad lines, high-energy signatures, compactness, variability where possible, and spectral shapes that stars alone struggle to explain. If a galaxy seems too massive, refine the stellar population model, check for dust, examine lensing, search for emission line contamination. If reionization appears patchy, measure galaxies in different environments and compare them with the state of surrounding hydrogen. If expansion remains mismatched, strengthen both local and early universe measurements until one side bends or the model does. The work is slow because the universe is not close. A laboratory physicist can adjust conditions and run another experiment. Cosmologists cannot change the universe and watch again. They can only look in more directions, with more sensitivity, across more wavelengths, using natural experiments created by gravity and time. A galaxy cluster can become a lens. A supernova can become a distance marker. A spectral line can become a clock. A background temperature ripple can become a fossil of sound waves in the early plasma. Everything available is indirect. Yet indirect does not mean weak. A shadow can reveal a body. A fingerprint can identify a hand. A stretched wavelength can locate a galaxy in time. The universe is not handing over objects, it is handing over consequences. Webb is powerful because it catches consequences from closer to the first light than ever before. That closeness changes how the past feels. The early universe is no longer a far abstraction behind a wall of equations. It is becoming observational terrain. It has regions, populations, outliers, confirmed distances, failed candidates, emission lines, compact sources, questions that can be assigned to telescope time. That is a transformation in human knowledge. A territory once described mainly by inference now has landmarks, even if many are faint and contested. Landmarks change maps. They do not always destroy them. Sometimes they correct coastlines. Sometimes they reveal a river where the map showed desert. Sometimes they expose a mountain range hidden under cloud. The old map still guides travel, but it can no longer pretend the blank areas are understood. Webb has placed landmarks in cosmic dawn, and some of them do not sit comfortably where the map expected flat ground. A mature response does not tear up the map. It takes out a sharper pencil. That may sound modest, but it is not. The history of science is full of sharper pencils that changed everything. Better measurements of planetary motion exposed cracks in old celestial mechanics. Better spectra revealed the chemistry of stars. Better galaxy observations expanded the known universe beyond the Milky Way. Better supernova distances revealed accelerating expansion. In each case, reality did not become dramatic because someone shouted. It became dramatic because a measurement refused to be decorative. Webb's measurements are beginning to refuse decoration. They are no longer just beautiful images for the public imagination. They are constraints with consequences. They are early light asking modern theory to account for its arrival. They are the universe saying that the first chapter contains more activity than the summary suggested. And a summary is never the same as the book. A summary is useful until the book begins to contradict it. For a long time, the first billion years of cosmic history could be summarized with broad confidence because the details were thin. The universe cooled, atoms formed, darkness followed. Gravity built the first structures. Stars and galaxies appeared. Their radiation cleared the fog. Larger galaxies grew from smaller ones. That outline remains powerful, but Webb is pressing into the verbs. Cooled how? Gathered how fast? Appeared in what numbers? Cleared the fog with which sources? Grew by what paths? The outline survives only if the verbs become more precise. Precision is where comfort goes to be tested. A vague early galaxy can fit almost anywhere. A confirmed galaxy, with a measured redshift, a strong emission line, an estimated stellar mass, and a place in a growing population, has less freedom. It begins to demand a specific past. If stars made the light, the star formation history must be plausible. If dust reddened the source, earlier stars must have already made the dust. If a black hole contributed, some seed must have formed and fed. Each interpretation spends time from the cosmic budget. The budget is tight. Not impossibly tight, but tight enough that waste matters. A model cannot casually add long delays. It cannot let gas sit idle too long before forming stars. It cannot wait many generations before producing dust, if dust is already hinted in early objects. It cannot grow black holes at a leisurely pace, if active nuclei are common near cosmic dawn. The universe may have had hundreds of millions of years, but the work being asked of those years was immense. That is why Webb's evidence has a physical tension that numbers alone can hide. A redshift does not feel like a deadline until it is translated into events. A galaxy at that age means the universe had already built a gravitational home for gas. It had already made that gas cold and dense enough to ignite. It had already created stars bright enough to be seen across almost all of time. If the system looks chemically evolved, then some stars had already died and returned material. If it contains a black hole, then collapse and feeding had already begun. The signal is small. The required history is not. That mismatch between appearance and implication gives the subject its pull. Webb's early sources often look visually modest. They do not overwhelm the eye like nearby nebulae or spiral galaxies. Many are marks on a dark field. Their drama is hidden in the timestamp. A faint red object becomes powerful because of when its light left, not because of how it looks now. It is a whisper from a room we expected to be quieter. The room keeps producing noise. Some of that noise may come from black holes. This possibility changes the story without simplifying it. A black hole does not shine by itself. The bright signal comes from matter falling toward it, heating as it accelerates and compresses. Around a feeding black hole, gravity turns infalling gas into radiation with terrifying efficiency. If such engines were already common in young galaxies, then early cosmic history included compact power sources capable of altering their hosts. That would solve one problem by opening another. If black holes explain the brightness of some early red sources, then those galaxies may not be as overgrown with stars as first assumed. The stellar mass problem softens, but now the black hole problem sharpens. Where did the seeds come from? Were they remnants of the first massive stars? Did some gas clouds collapse directly into heavier seeds? Did dense star clusters build them through mergers? How rapidly could they feed without blowing away their own fuel? A black hole is not an answer. It is a new clock. Its growth must fit the available time too. Small seeds need sustained feeding to become large. Heavy seeds need special formation conditions. Rapid feeding can be limited by radiation pushing gas away. Mergers can help, but they require crowded environments and time. So when early black holes appear in the conversation, they do not remove the pressure from cosmic dawn. They redistribute it from stars to gravity's darkest engines. That redistribution may be one of Webb's major legacies. It is forcing astronomers to ask whether the first galaxies and the first black holes grew together from the beginning, rather than one simply following the other. In nearby massive galaxies, central black holes and their hosts seem linked in long-term evolution. The relationship is complex, but it suggests a conversation between star formation, gas flows, and black hole feeding. Webb may be showing early fragments of that conversation at an age when the participants should barely have found their voices. If that is true, the first galaxies were not just nurseries of stars. Some were already negotiating with monsters at their centres. The word monster should be used carefully. A black hole is not evil, not hungry in the human sense, not a cosmic animal. But the physical extremity is real. A region smaller than a solar system can influence light from an entire young galaxy if enough material falls inward. Gravity can concentrate power so tightly that a small centre changes the interpretation of the whole object. For Webb, that means a tiny source can blur the line between a galaxy that is massive and a galaxy that is centrally lit. This is why the little red dots matter. They are not valuable because they sound mysterious. They are valuable because they confuse categories in a measurable way. Some may be compact galaxies, some may be active black holes, some may be dusty systems, some may be combinations where stars and black hole light are tangled beyond easy separation. Their existence says the early universe had small, intense sources that our older categories may not divide cleanly. A category failure is not a failure of science. It is often the first sign that nature is being seen at higher resolution. When a blurry object sharpens, it does not always become the thing we expected. It may become several things. It may become a hybrid. It may reveal that our old labels were built for a later, calmer universe. Webb's compact sources could be doing that for cosmic dawn. They may be showing a phase where dense stellar systems, dust, gas, and black hole activity overlapped in ways that are rare or less visible today. That possibility changes the kind of model needed. A simple model with smooth star formation will not be enough. A simple black hole growth curve will not be enough. A simple reionization timeline will not be enough. The early universe may require models that handle bursts, leakage, obscuration, compactness, environmental patchiness, and rare fast growth all at once. Not because complexity is fashionable, but because the evidence may demand it. The danger is that complexity can become a hiding place. If a model can be adjusted endlessly, it stops being brave. The best models remain exposed. They predict population counts, brightness distributions, spectral features, black hole fractions, chemical signatures, and reionization histories that can be checked. Webb's discoveries are important because they make those checks harder to avoid. They replace broad stories with sharper obligations. That is the pressure behind the next stage of the field. The first years of Webb gave astronomy shock and orientation. The next years demand discipline. More spectra, more careful masses, wider fields, better simulations, stronger separation between stars, dust, gas, and active nuclei, better links between early sources and later descendants. The mystery must become less glamorous in language and more rigorous in structure. Only then will the real anomaly remain visible. If it remains, it will have survived the hardest part of discovery, being made less dramatic by better knowledge and still refusing to disappear. That is the stage where a field begins to change its posture. At first, the surprising result is handled with distance. Then it becomes a nuisance, then a constraint. Then, if it keeps surviving, it becomes a fact that future theories must begin with, rather than explain away. No one can decide in advance whether Webb's early tensions will reach that final stage, but the path is now open, and that alone shifts the center of gravity. The first galaxies are no longer decorative unknowns. They are becoming judges. They judge the recipes for star formation. They judge the assumed brightness of early stellar populations. They judge the possible role of black holes. They judge how radiation escaped into space. They judge whether simulations can pass through cosmic dawn and still arrive at the later universe intact. They judge the patience of scientists who must separate what is real from what is merely exciting. That last judgment may be the most important, because the universe is not only testing theories, it is testing our appetite for certainty. A sensational answer is emotionally easy. A dismissal is also easy. The harder position is to let the evidence remain unresolved without turning it into fog. To say, this part is confirmed, this part is inferred, this part is model dependent, this part is still debated, and this part may become important if it survives the next tests. That honesty does not weaken the wonder. It gives the wonder a spine. A parallel universe claim collapses if the evidence does not support it. A careful frontier grows stronger as evidence accumulates. Webb's deepest discoveries belong to the second kind. They do not need to prove another reality. They force a confrontation with this one. The universe we actually inhabit may be less tame near its beginning than our models allowed. That is enough to unsettle the whole story, especially because the story was already under stress. The Hubble tension did not begin with Webb, but Webb made one of its easy exits narrower. The local measurement ladder had been accused of possible crowding or calibration issues in older data. Webb's infrared sharpness gave astronomers a cleaner look at some of the same distance markers. The disagreement did not quietly vanish. It remained close enough to the old result that the tension kept its place at the table. The field did not receive a solution. It lost a comfort. That loss matters. Many scientific revolutions begin not with a new answer, but with the removal of an old excuse. As long as an anomaly can be blamed on a likely error, the larger model sleeps easily. When the likely errors are checked and the anomaly stays awake, the room changes. The model may still be right, the measurements may still hide some subtle issue, but the question acquires weight. The Hubble tension is weight without image. No glowing galaxy, no red dot, no dramatic deep field picture. Just two routes to the expansion rate of the universe refusing to meet where they should. One route begins with the early universe and the cosmic microwave background, then uses the standard model to infer today's expansion. The other climbs outward from nearby distance markers and exploding stars. Both are sophisticated, both have histories of scrutiny. Their mismatch is not huge enough to look absurd, but it is persistent enough to feel accusatory. Webb's early galaxies give that accusation a setting. They do not prove the same cause. They do not have to. They simply remind us that the first chapters of cosmic history are now under direct inspection, and those chapters are not behaving with the quiet simplicity once assumed. If the expansion story also contains an unresolved mismatch, then the young universe becomes a place where multiple lines of pressure converge, even if the final explanations differ. Convergence is not proof. It is attention. The attention now falls on the first billion years, not as a vague ancient period, but as an active arena where structure, radiation, chemistry, black holes, and expansion history all intersect. This is where the earliest galaxies begin to shine. This is where the hydrogen fog begins to clear. This is where the first heavy elements spread into gas. This is where black hole seeds may begin their climb. This is also where any hidden early energy component, if such a thing existed, would have left traces in the later expansion record. A small change there can echo. But echoes are difficult to interpret. A sound in one room may come from a footstep, a pipe, a settling wall, or a door closing somewhere else. Cosmology faces the same problem in a grander form. Early galaxy brightness, reionization, black hole growth, and expansion tension may not share one cause. The universe may be presenting several difficult problems at once. It may be messier than our desire for one elegant solution. That possibility should not disappoint us. A messy universe is still a lawful universe. It simply refuses to arrange its questions for our convenience. The first galaxies may require improved astrophysics. The expansion tension may require improved measurement or new cosmology. Little red dots may divide into several populations. Reionization may turn out to depend on faint galaxies more than bright ones. Each thread may lead somewhere different, and the true map may be a woven structure rather than a single arrow. The danger is mistaking unity for depth. One grand explanation can feel deep because it simplifies, but a careful account can be deeper if it preserves the real complexity. The young universe may not be sending one message, it may be sending many, each carried by a different kind of light. Starlight says one thing, gas emission says another, dust changes the tone. Black hole activity adds another voice. Expansion stretches them all before they arrive. Webb hears the chorus before we understand the score. That is why the next generation of interpretation matters. The telescope has already expanded the archive. Now the field must learn how to read it without overreading. Not every bright early galaxy is a crisis. Not every compact red source is a black hole. Not every model mismatch is new physics. But not every surprise is a mistake either. A mature science has to keep both refusals alive. Refuse exaggeration. Refuse complacency. Between those refusals, the real work begins. Models of stellar populations will be rebuilt for metal-poor early environments. Simulations will test more bursty histories. Black hole seed scenarios will be compared against the growing census of compact sources. Reionization models will use Webb's faint galaxies to ask how much light escaped. Distance ladder measurements will keep tightening. The cosmic microwave background will remain a stern witness, allowing only certain changes to the early universe. Every witness matters because the universe is one event. Not one object, not one scene, one unfolding. The microwave background is not separate from the first galaxies. The first galaxies are not separate from the chemical richness of later stars. Later stars are not separate from the planets that form around them. The expansion rate is not separate from the distances we assign to ancient light. Each measurement is a surviving surface of the same deep history. That is the real reason the Webb discoveries feel larger than astronomy news. They touch the continuity of everything. The light from early galaxies is not only old, it belongs to the era when the universe began preparing the conditions for every later kind of structure. The first heavy elements did not know they would become worlds. The first black holes did not know they would become clues. The first bubbles in the hydrogen fog did not know they would one day be modelled by minds made from stellar debris. But the chain is real. We are late products of the very processes we are trying to reconstruct. That gives the investigation a strange intimacy. Webb is not only looking outward, it is looking backward along the ancestry of matter. Not to life directly, not to Earth, not to anything human, but to the first cosmic habits that made later complexity possible. Gathering, burning, enriching, clearing, collapsing, feeding, expanding. If those habits began earlier or ran harder than expected, our origin story changes tempo. Not its basic direction. Its tempo, once changed, changes the feeling of the whole piece. A melody can have the same notes and still become unfamiliar if it begins faster than expected. Cosmic history is like that. The ingredients may remain the same: gravity, gas, dark matter, radiation, expansion, stars, black holes. Yet if the first luminous structures appeared earlier, burned harder, and influenced their surroundings faster than our models assumed, then the opening movement of the universe has a different character. The story does not need new mythology, it needs a better rhythm. Webb is measuring that rhythm in infrared light. Not as a grand theory, but one object at a time. A galaxy's redshift places it on the cosmic clock. Its brightness suggests how much energy it released. Its spectrum hints at gas, stars, and sometimes active centers. Its color may reveal dust, age, or distance. Its compactness may point toward dense, early assembly. Its environment may tell whether the surrounding hydrogen had already been altered. Slowly, these features become a pulse. How often bright systems appear, how quickly they grow, how much light they leak, how strongly they shape the young universe. That pulse is not smooth. It may never have been smooth. The earliest galaxies likely formed in bursts, not in calm, continuous growth. Gas gathered, ignited, got disrupted, fell back, ignited again. A small system could spend much of its life faint, then briefly flare into detectability. This matters because telescopes do not see a galaxy's whole life. They see a moment. If cosmic dawn was full of flickering systems, then the population Webb detects is shaped by timing as much as by mass. A flare can make a small thing look large. That single fact can soften some early tension. It can explain why objects look brighter than their mass might suggest. But it does not remove the need to explain why so many flares occurred, how long they lasted, what triggered them, and whether they produced enough radiation to matter beyond their own galaxies. A flickering universe is still a demanding universe. It asks for models that treat early light as episodic, directional, and tied to violent feedback. The word feedback sounds technical, but the image is simple. A galaxy gives birth to stars, and those stars immediately begin damaging the place that made them. Their radiation heats gas. Their winds push material outward. Their deaths explode through the surrounding clouds. That damage can slow future star formation by blowing gas away. It can also create openings where radiation escapes. In a small young galaxy, the balance is delicate. Too much violence, and the galaxy loses its fuel. Too little, and its light remains trapped. Cosmic dawn may have depended on that balance. Not only on how many stars existed, but on whether their energy escaped into the wider universe. A galaxy sealed by its own gas is bright from the inside and less important outside. A galaxy torn open by its own stars can leak radiation into the intergalactic medium. That leaked radiation helps ionize hydrogen. It changes the transparency of space. It participates in the end of the cosmic fog. So the same violence that threatens a young galaxy may also make it cosmologically important. This is the kind of detail that turns the early universe from a timeline into a living system. The first stars are not just markers of progress, they are agents of instability. The first black holes are not just curiosities, they may alter light, gas, and growth. The first dust is not just a sign of chemistry, it changes what future observers think they see. Every ingredient acts and interferes. A simple diagram cannot hold that easily. But a good model eventually must. The challenge is that Webb sees consequences more easily than causes. It can detect light from a system. It can measure features in that light. It can show that the system existed at a certain time. But the full internal life of that galaxy, the shape of its gas, the exact arrangement of stars, the hidden black hole if one exists, the channels through which radiation escaped, remains partly inferred. The first galaxies are too distant to examine the way we examine nearby galaxies. Their secrets come compressed. Compression creates ambiguity. An early red source may be old in its stellar population, or dusty, or powered by a black hole, or affected by strong emission lines, or some mixture. A luminous galaxy may be massive, or temporarily bright, or magnified. A compact shape may indicate density, or simply the limits of resolution. The deeper Webb looks, the more it must distinguish between physical extremity and observational disguise. That task is not a weakness of the telescope. It is the price of time travel by light. To look back 13 billion years is to accept that the universe will not give us easy angles. It will give us stretched wavelengths, faint flux, crowded fields, foreground distortions, and objects too small to resolve in familiar detail. Human beings then build methods around those limits. They compare filters, they take spectra, they stack populations, they model stellar histories, they search for patterns that do not depend on one fragile interpretation. Patterns are the way out. A single ambiguous source can only suggest. A population can speak. If many sources share similar traits, if their redshifts are confirmed, if their number density remains high after corrections, if simulations still struggle to reproduce them, then the evidence becomes less dependent on any one object's uncertainty. The pressure becomes statistical, not anecdotal. That is where Webb's future power lies. The early years gave the shock of access. The next years will decide the shape of the pressure. More fields will be surveyed, more spectra will confirm or reject candidates. The faint population will be better constrained. Compact red sources will be sorted. Black hole signatures will be tested. Reionization models will be forced to account for real galaxies, not only assumed ones. The first billion years will become less mythical and more measured. Measured does not mean drained of wonder. A measured mystery is often the most durable kind. It cannot be waved away as imagination. It has coordinates, uncertainties, competing explanations, and future tests. It becomes part of the working world of science. The public may lose the first thrill when the words become more cautious, but the actual discovery deepens. The question stops being, did Webb find something impossible? And becomes, what must the universe have been like for these measurements to be true? That question cannot be answered by excitement. It has to be answered by reconstruction. Reconstruction begins before the first stars. The cosmic microwave background shows a universe almost uniform, but not perfectly. Those tiny imperfections were the seeds. Dark matter responded to gravity and amplified them. Ordinary matter followed, heated and cooled, resisted and collapsed. The first halos formed. Some remained too small to make lasting light. Some crossed the threshold. The earliest stars ignited, lived quickly, and died into the gas around them. The next structures inherited that changed material. By the time Webb sees the first bright galaxies, the story is already underway. That is why every early detection carries invisible history. It points backward to dark matter assembly. It points inward to gas physics. It points forward to reionization and later galaxies. It is not a standalone marvel. It is a knot in the entire rope. Pull on it, and the rope moves through almost all of cosmic time. That is what makes the early universe dangerous to simple stories. It is not safely sealed behind us. Its conditions echo into everything later. The first galaxies affect reionization. Reionization affects how light travels afterward. Early enrichment affects later stars. Early black holes affect the growth of massive galaxies. Expansion history affects the distances we infer for everything. A small error near the beginning can become a large misunderstanding when stretched across 13 billion years. This is why a telescope can make an old theory feel young again. Einstein's equations are more than a century old, but Webb is using them in a region of cosmic history that Einstein could not observe. The theory helps interpret the redshift of light. It helps describe expansion. It explains gravitational lensing, where mass bends the path of light and can magnify distant galaxies. It gives black holes their modern meaning. The discoveries do not stand outside that framework, they lean on it. So the more precise statement is not that Webb shattered Einstein. It is that Webb is testing the cosmic architecture built with Einstein's tools in places where the scaffolding is hardest to inspect. That architecture includes things Einstein did not know would become central: dark matter, dark energy, the cosmic microwave background, the statistical distribution of galaxies across the sky, the detailed history of reionization, the growth of supermassive black holes. The first billion years have become a kind of trial ground, where the broad success of modern cosmology must prove it can handle the messy birth of visible structure. A broad success can hide local weakness. A city map can show every highway and still be wrong about the alleys where people actually live. Lambda CDM, the standard cosmological model, is extraordinary on large scales. It describes a universe whose structure grows from early fluctuations under gravity, with dark matter providing most of the clustering mass and dark energy shaping late expansion. But the first galaxies live in the alleys of that model. They depend on gas, cooling, radiation, feedback, dust, black holes. and the details of how light escapes. Webb walked into those alleys. They were busier than expected. That busyness may be explainable without changing the large-scale map. The alleys may simply need better detail. Star formation in small early systems may be more violent. The first stellar populations may produce more light. Feedback may make galaxies flicker. Black holes may contribute to compact red sources. Dust may appear in pockets sooner than broad intuition suggests. Lensing may magnify some of the most dramatic examples. Survey statistics may shift as the sample grows. All of that would still be a major advance. It would mean the early universe was not impossible, but underestimated. It would mean the laws were not wrong, but the consequences of those laws under young, dense conditions were sharper than expected. A model does not have to collapse to be transformed. Sometimes it becomes more powerful because an instrument forces it to stop being vague. That may be the most likely future. But the deeper possibility remains in the room because of the expansion problem. The Hubble tension keeps the lower structure from feeling completely settled. If local measurements of expansion and early universe inferences continue to disagree, and if every careful check fails to remove the mismatch, then cosmology may need a new ingredient or a new relation among old ingredients. Not a wild invention, something specific enough to pass all the existing tests and still explain the discrepancy. That is a narrow path. Most new ideas do not make it through. Early dark energy, for example, is attractive because it tries to alter the early expansion history briefly, then fade. It may help shift the inferred expansion rate, but it cannot simply be added like seasoning. The cosmic microwave background is exquisitely measured. Galaxy clustering imposes constraints. The age and growth of structures respond. A proposed solution must move one stubborn number without disturbing the rest of the cosmic accounting too much. That difficulty is not discouraging. It is protective. Without those constraints, cosmology would become storytelling with equations. With them, it remains science. Every serious proposal has to risk failure in public view. It has to say not only what it explains, but what else should be true if it is right. It must invite future observations to kill it. Webb's early galaxies now serve as part of that killing ground. If a new model changes the early universe, it must still produce the galaxies Webb sees. If it speeds up expansion at the wrong time, it may make structure harder to form. If it alters dark matter behavior, it may change the abundance of early halos. If it changes the growth of perturbations, it must still match later surveys. Cosmic dawn is no longer a blank where new physics can hide without consequence. It has lights in it. The lights are witnesses. They do not speak loudly, but they speak from a time when the universe was still setting the terms for everything after. Their testimony is faint, stretched, and difficult, yet it is real enough to complicate the clean lines of theory. That complication is the true title payoff. Webb did not find a different universe outside ours. It found a younger version of our universe that behaves differently enough to make our adult expectations unreliable. A child is not a different species from the adult. But you cannot understand childhood by studying only adults. That is the mistake cosmic dawn may be exposing. We've built much of our physical intuition from the later universe, where galaxies have had billions of years to mature, where metals and dust are widespread, where space is transparent, where black holes have grown into familiar relationships with their hosts. Then Webb looked at the childhood of galaxies and found systems that did not politely follow adult expectations. They flickered. They burned. They may have fed black holes. They altered their surroundings before the rest of the universe had fully cleared. That does not make them fully mature. It makes them active children in a violent environment. The difference matters. Calling them mature can mislead. Calling them impossible can mislead more. The better phrase is physically consequential. They were young, but they already mattered. They could produce light, enrich gas, help clear fog, and perhaps host compact engines of gravity. A young thing can be unfinished and still change the room. Cosmic dawn seems to have been full of such unfinished powers. The first stars did not need to last long to change chemistry. Massive stars burn fast, die fast, and seed their surroundings. The first galaxies did not need to be large to affect reionization if enough radiation escaped. Black holes did not need to reach their final masses to complicate the interpretation of early light. Each process could begin small and still set direction. This is how the universe builds significance before grandeur. It does not wait for spiral arms to become beautiful. It does not wait for planets to form. It does not wait for galaxies to become majestic. It begins with thresholds, a halo deep enough, a cloud cool enough, a star hot enough, a channel open enough, a black hole fed enough to shine. Webb is catching thresholds, not finished monuments. Thresholds are harder to photograph emotionally. They do not always look spectacular. They are crossings, before and after. Dark gas becoming luminous, neutral hydrogen becoming ionized, pristine matter becoming enriched, a hidden halo becoming a visible galaxy, a black hole seed becoming an active source, a model assumption becoming a measurement problem. That last threshold belongs to us. It is the point where human confidence becomes testable. We had a picture of how the first light should appear. Webb brought back evidence. Some of the picture held, some of it bent. Now the question is whether the bending is local, structural, or deeper than anyone can yet prove. The answer will not come from one red dot. It will come from the pattern left when thousands of red dots, spectra, failed candidates, confirmed galaxies, black hole signatures, reionization maps, and expansion measurements are forced into the same history. That history must be coherent. It must explain why the beginning looked the way it did, why the later universe looks the way it does, and why our measurements of expansion still do not sit as comfortably together as they should. Coherence is the prize, not drama. A dramatic story can be built quickly. A coherent one takes years. It survives correction because it was never dependent on one sensational claim. Webb's best legacy may be that it turns the sensational into the accountable. The word different becomes testable. Different how? Brighter by how much? More numerous at what redshift? Powered by what source? Consistent with which model? In tension with which measurement? Solvable by which physical change? Every vague thrill becomes a question with teeth, and those teeth are what keep the story from dissolving into spectacle. The word different has to be earned. If it means another universe, the evidence is not there. If it means a young phase of our own universe operating under conditions so extreme that adult galaxy intuition fails, then the word becomes useful. If it means early structure formed with more speed, brightness, leakage, and black hole involvement than expected, the word becomes testable. If it means the expansion history contains a missing ingredient, the word becomes dangerous in a deeper way. Each meaning carries a different burden of proof. Webb has not carried all those burdens. It has placed them on the table. That may sound less satisfying than a final revelation, but it is more faithful to the moment. The telescope has changed the conversation by making old generalities inadequate. A broad model saying galaxies form early is no longer enough. How early? How bright? How many? How massive? How dusty? How black hole lit? How much ionizing radiation escapes? How do these objects connect to later galaxies? How do they fit beside a universe whose measured expansion still contains a stubborn disagreement? The questions are multiplying because the evidence is improving. Improved evidence does not always make reality simpler. Often it makes the first simple version impossible to keep. A blurred face can be described in a sentence. A clear face has expression, age, scars, asymmetry, and mood. Cosmic dawn was blurred for a long time. Webb has not made it fully clear, but it has given it features. Those features now have to be explained, not smoothed back into the old outline. The outline will survive only by becoming more specific. That is how knowledge matures. It does not remain pure. It takes on exceptions, regimes, limits, hidden assumptions, and revised mechanisms. Newton's laws became the low-speed, weak gravity truth. Einstein's theory became the deeper language of gravity, while still leaving cosmology with dark components whose nature remains unknown. Lambda CDM became the best large-scale recipe, while galaxy formation remained a field of difficult subgrid physics and uncertain early behavior. Webb is forcing the early behavior to grow up. It is taking what had been a theoretical infancy and giving it observational pressure. It asks models to stop treating the first galaxies as generic small objects and start treating them as measured systems with peculiar light, possible dust, possible black holes, and real consequences for reionization. It asks whether cosmic dawn was driven by rare bright sources, numerous faint ones, or a combination whose balance changes with time and environment. It asks whether the first billion years were a slow ramp or a jagged sequence of bursts. A jagged sequence would explain why the early universe feels so hard to summarize. Some galaxies could be caught in flares. Some could hide behind dust. Some could be magnified. Some could leak radiation efficiently. Some could shut themselves down temporarily after blowing out gas. Some could host central engines that distort our estimate of their stellar mass. The population would not line up neatly. It would scatter. That scatter is not noise if it reflects real physical variety. The scatter may be the signal. A car model may predict averages that look reasonable, then fail at the extremes. Webb's early discoveries often live near those extremes: unusually bright, unusually compact, unusually red, unusually early. Extremes matter because they reveal the speed limits of a theory. The average galaxy may be easy to produce. The rare intense one may expose which assumptions are too slow. But extremes can also fool. A rare object found in a small field may look more common than it is. A magnified galaxy may look intrinsically brighter. A source with black hole light may masquerade as stellar mass. A strong emission line may inflate a broadband measurement. This is why the field must move from spectacle to distribution. The question is not whether any strange early object exists. The question is how the whole population behaves once the biases are understood. Population is where the model stands trial. Not in a single image, but in the shape of many counts. How many galaxies at each brightness? How those counts change with redshift? How many show signs of dust? How many have spectra confirming distance? How many may contain active nuclei? How many faint sources are required to complete reionization? A model that passes these tests has earned something. A model that fails them cannot hide behind elegance. Elegance is beautiful. But the early universe may have been ugly in exactly the way reality often is. Uneven, tangled, full of competing processes, hard to compress into a clean line. The first stars may have been born in clusters that quickly disrupted their own nurseries. The first black holes may have grown in rare dense pockets. Radiation may have escaped through temporary cracks. Dust may have appeared early in some galaxies and not in others. One region might race ahead, while another remained nearly dark. There is no reason the beginning had to look organized to us. Organization came later, partly because chaos had time to build structure. Spiral galaxies, stable disks, mature stellar populations, long-lived planetary systems, these belong to a universe with billions of years behind it. Webb is peering into a time when the assembly was still loud. The fact that some early systems appear compact and intense should not surprise us emotionally, even if it challenges calculations. Youth can be violent. Still, violence alone is not an explanation. The physics must close. Energy must come from somewhere. Gas must be available. Gravity must gather it. Radiation must escape or be absorbed. Stars must produce the observed light. Black holes must have a growth path. Dust must have a source. Every vivid image has to pay its physical bill. That is what prevents this story from becoming empty cosmic poetry. The bill is the discipline. It is tempting to say the first galaxies were too mature. Sometimes that phrase points in the right direction, but it can also mislead. Many early systems were not mature in the sense of being settled, grand, and chemically rich like later galaxies. Their strangeness may be almost the opposite. They were immature systems behaving with short-lived intensity. They were not old cities. they were construction fires. A construction fire can illuminate a whole site without meaning the city is complete. That image protects the central truth. Webb's early objects may look bright not because they had finished growing, but because they were in violent phases of growth. Their light may be the glare of assembly, not the glow of maturity. That distinction matters for both accuracy and emotion. It keeps the awe tied to process rather than exaggeration. A process can be more powerful than a finished thing. A forming galaxy is a place where matter is being converted into future history. Hydrogen becomes stars. Stars become heavy elements. Heavy elements become dust, planets, chemistry. Radiation alters the transparency of space. Black holes, if present, reshape gas and light. The first galaxies are not important because they resemble the Milky Way. They are important because they begin the chain that eventually makes galaxies like the Milky Way possible. That chain gives Webb's ancient light an intimate edge. The telescope is not only looking at distant objects, it is looking at early stages of the material ancestry of complexity. The carbon in living tissue, the oxygen in water, the silicon in rock, the iron in blood. None of these were abundant at the beginning. They had to be made. The universe had to pass through generations of stars before such materials could become common. If Webb shows that enrichment began quickly in some places, then our matter's long prehistory begins earlier in the cosmic score. Not life. Not planets. The preconditions. That restraint matters. Early galaxies do not imply early life. They do not make the young universe habitable in any simple sense. They mark the beginning of processes that later, after billions of years, allow rocky worlds and chemistry to become widespread. The emotional force comes from the distance between those stages. A faint red galaxy near cosmic dawn is not our home, but it belongs to the deep chain, without which home would not exist. The universe becomes more intimate when the chain is visible. Not smaller. More connected. Webb's ancient sources sit at the far end of that connection. Their light began before the sun, before Earth, before any atom in a human body had joined the form we now inhabit. It travelled while other stars made the elements that would later form planets. It arrived after a species made of those elements built a telescope to catch it. There is a loop there, but it should not be sentimentalized. It is not destiny. It is consequence. Matter became capable of asking where matter came from. Then it found evidence that the earliest visible steps may have been faster than expected, and that is where the story finally settles into its real shape. Not into certainty, into responsibility. A discovery like this gives the imagination permission to move, but not permission to run wild. Webb's ancient galaxies ask for wonder, and then immediately ask for discipline. The light is too old, too faint, and too important to be used carelessly. If the young universe was more active than expected, the task is not to shout that everything has collapsed. The task is to learn which assumption was too slow, too smooth, too modern, or too confident. Perhaps the first galaxies formed stars in sharper bursts than our models allowed. Perhaps the earliest stellar populations were brighter for their mass. Perhaps some compact red objects are powered by black holes that began growing sooner than expected. Perhaps some apparent mass is really light from hidden central engines. Perhaps dust appeared in pockets quickly because the first massive stars lived fast and died early. Perhaps faint galaxies, still difficult to count, did more of the work of clearing the cosmic fog than the bright objects that first caught our attention. Perhaps the Hubble tension is a separate problem, waiting for its own explanation. Perhaps it is not separate. The honest frontier is made of those perhapses. Not all of them will survive. Some will shrink under better data, some will split into smaller questions, some will become technical details. One or two may harden into something future cosmology cannot avoid. That is why this moment matters. It is not the end of the model. It is the beginning of a more demanding version of the model. A weaker story would end by declaring victory over Einstein. A better story ends with Einstein still standing, but no longer surrounded by the illusion that the universe is finished. His theory gave gravity a language deep enough to describe expanding space, bending light, black holes, and the large-scale behavior of the cosmos. Webb is not humiliating that language. It is using it to read a page written in conditions Einstein never saw. If that page contains unfamiliar grammar, the answer is not to burn the book. The answer is to keep reading until the grammar becomes clear. That is the work now. To read cosmic dawn without turning it into myth. To follow early light without pretending every red dot is a revolution. To admit that some models were too comfortable without pretending all knowledge has failed. To let the universe be strange in the exact way the evidence allows. Exact strangeness is stronger than vague awe. Vague awe says the universe is mysterious and leaves the mind where it was. Exact strangeness says a galaxy at this redshift, with this brightness, under these assumptions, requires this much star formation, this possible black hole contribution, this kind of dust, this escape of radiation, this relation to the surrounding fog. It gives the mind something to hold. It turns wonder into pressure. Webb has given cosmology that pressure. It has made the first billion years less blank. It has placed objects inside the dark. It has shown that some early systems were already capable of changing their surroundings. It has added weight to the idea that black holes may have entered the story early. It has forced galaxy formation models to deal with sharper evidence. Beside all of that, the expansion tension continues to sit like an unresolved note, quiet but impossible to ignore. The universe has not confessed to being different. It has become harder to treat as already understood. That is a subtler ending, but it lasts longer. Sensational claims burn out when the next correction arrives. A careful tension survives correction because it was never built on the loudest version of itself. Webb's strongest message is not that one impossible thing appeared. It is that the young universe is now visible enough to resist us. Resistance is how knowledge grows. The universe resists our first sketches. Then it resists our better diagrams. Then it resists our simulations. Each resistance removes laziness. It forces a clearer relation between evidence and belief. It asks us to say what we know, how we know it, and where the picture still shakes. Right now, the picture shakes near the beginning. Not everywhere, not catastrophically. In specific places. The abundance of early bright galaxies. The nature of compact red sources. The pace of black hole growth. The role of faint galaxies in reionization. The escape of radiation. The exact expansion rate of the present universe inferred from the ancient one. These are not random cracks. They are stress lines across the first chapters of cosmic history. Stress lines are not failure. They are information. A bridge under load reveals where its hidden forces are. A theory under observation reveals where its hidden assumptions live. Webb has added load to the bridge. The bridge still stands. That is why the stress is worth studying. If it had collapsed instantly, there would be nothing precise to learn. If it showed no strain, there would be nothing new to ask. Instead, it holds and trembles. That trembling is the sound of a field becoming more honest. The early universe was never obligated to match our cleanest version of it. It did not know our diagrams. It did not wait for our categories. It gathered matter, made stars, fed black holes, carved holes in hydrogen, enriched gas, stretched light, and carried its own evidence forward until a cold telescope could receive it. The evidence arrived without caring whether it would comfort us. That is why the final feeling should not be fear. It should be attention. Attention to the faint. Attention to the revised. Attention to the measurement that refuses to move. Attention to the object that becomes less dramatic but still remains important. Attention to the difference between a model being wrong and a model being incomplete. Attention to the way reality can be lawful and still exceed the habits built from later, calmer conditions. The young universe was not another universe. It was ours before it became familiar. That may be the deepest correction Webb offers. Familiarity is not truth. It is only repeated exposure. We know the nearby universe better, so we mistake it for the standard by which all cosmic behavior should be judged. Webb has looked back to a time before that familiarity existed and found a world of first attempts. First galaxies bright enough to reach us, first heavy elements spreading through gas, first radiation leaking into the fog, first black holes perhaps beginning their rise, first structures turning invisible gravity into visible history. The first attempts were not gentle. They were compressed, uneven and costly. Stars burned through fuel, some exploded, gas was heated and expelled, light was trapped, then escaped. Gravity built centers of power, space stretched every signal. The universe began making the conditions for later complexity through processes that were violent long before anything existed to suffer them. There is no need to exaggerate that. The plain version is already immense. A faint infrared signal lands on a mirror. In that signal is a galaxy from near the opening of time. In that galaxy is evidence of matter organizing quickly enough to trouble our expectations. Around that evidence are uncertainties, corrections, competing models and future tests. Behind it stands a century of theory, not defeated, but summoned back to work. That is what Webb found. Not a doorway out of reality. A demand placed on reality's best map. The map will change, maybe in small ways across many details, maybe in one deep way no one has yet proven. The only honest answer is that the change is still forming. But the direction of humility is clear. The universe is not done teaching the theories that claimed to describe it. The beginning, once blurred into a few broad sentences, now has enough detail to push back. And far from Earth, shielded from sunlight, colder than any human night, Webb keeps listening. It listens to light that left before there were planets like ours. It listens to galaxies that may have burned harder than expected. It listens to compact red sources whose true nature is still being untangled. It listens to the clearing of ancient fog, the growth of first structures, the early pressure of gravity and radiation. It listens without drama, without certainty, without caring what answer would make the better headline. The light comes in. The models answer. The light refuses some answers. That is science at its most beautiful. Not the destruction of knowledge, but its exposure to something older and less forgiving than itself. A universe that can still surprise us after Einstein is not a universe without order. It is a universe whose order is deeper than our first successful description. Somewhere near cosmic dawn, matter crossed a threshold and became visible. 13 billion years later, that visibility reached a machine we built to catch it. And now, because a few ancient photons arrived carrying more history than expected, the map of everything has to widen around them.